I guess, in a nutshell, that's what my talk's about. LVault is something I created, and I would love you to try it. And it's very simple. It's basically just those 4 lines. And I'll be coming back to those 4 lines, and maybe in the end of the talk you find it worthwhile to try it yourself. So first of all, who am I? I'm Henning Dietrich. I'm the founder and CEO of a small but very ambitious game company. Actually, I'm also working as a technical director for an event agency where we're doing all sorts of programming that has to do with shows and events. And I'm also the maker of LVault. So LVault, as you saw in the description, is a driver for VaultDB, which is a high-velocity database. And the reason why I got into this was because we were looking basically for the perfect game server. Now, that's probably something that will never exist, but it's where it comes from. That's also why I started to learn Erlang, because I had some experience with Java, and I found Erlang that gave the promise that these problems that I experienced with Java might be a thing of the past then. Same with VaultDB, because I had some experiences with MySQL, and I looked around for the best possible option to try to avoid these kind of problems in the future. So there was no driver for using VaultDB in Erlang, and I set about, actually 3 years ago, to write one. And I came up with one quite some time ago, and it was already used in production, also by a game company, but it was a purely synchronous driver. And basically, you can do a lot of stuff if you have a synchronous driver, but it's not really what this database is for. So we're going to look at VaultDB. What is that? Is it worth your time? Then at the driver itself and how you use it. And then we're going to look at a small sample and a benchmark. So last year, basically, I came here and had the opportunity to talk about the game server as a whole. And VaultDB is just one part of that game server. The other is Erlang and Lua. And last year, I had the announcement that there was an upcoming asynchronous version of the driver. And now, this year, I'm happy to come back and focus on that stable asynchronous version that I have, meanwhile, managed to put on GitHub. So what is VaultDB? In a nutshell, I would say, probably many of you have programmed with Redis. And Redis had this promise, we're going to have a Redis for clusters. Well, that never, it maybe will never be true in the way that you hope. But VaultDB, with a kind of a different approach, but with a lot of the same things like Redis, could be, in my view, called a Redis for clusters. Plus, they also kept many of the good things of SQL. VaultDB has a tail, and this is Mike Stonebreaker. And the points that he's making, he's very disruptive. He likes that word. And he's very strong in his presentations. But I think what's really important to know is that he's around in this database world for a long time. He's the guy behind Ingres, and he did Postgres. And he kind of knows what he's talking about. And what he's saying now is the time of the one-size-fits-all in databases is over. And he feels that we are in very exciting times that are reminding of the 70s when there were the database wars. And now we are seeing new databases coming up, and VaultDB really is his proposal for an OLTP database. So VaultDB is made by VaultDB Inc. That was founded in 2009. It was a development out of MIT in Berkeley, where they had experimental horizontally scaling sharding databases. It is open source. It's important to know it's created as dictatorial as Erlang. You won't have a say necessarily, but you can contribute. It's explicitly made for OLTP. It's not made to replace anything that you can do with MySQL, for example. If you look at CAP, we'll talk a little bit about that later. It's probably CA. It has some simple subset of SQL. It's in memory, but it also has a very good disk persistency. And it has ACID. And that's probably what was most important for me looking at it, because for games you often need a form of double bookkeeping that is very hard to do if you don't have ACID. So in a more general view, if we're not talking about games, if we're not talking about the intestines of the creature itself, from the business perspective, how they're positioning themselves as a product, they're saying basically, and I think that reverberates what we just heard, VaultDB is about big data and instant answers. So it's different than Hadoop. It's not so much about the way that you work with MapReduce, but you do have SQL queries, and you do have materialized views that are pretty good, pretty fast, and you let them run all the time. And that's why even if you have a very high data peak coming into the database, you'll have your answers really fast. From a technical point of view, VaultDB is just taking the pain out of scaling. Because if you're not Twitter and if you're not Facebook and you start out with MySQL, it might very well be that you won't have enough funding to overcome that moment when you have to have a cluster, because you have so much data that one server is not going to be enough anymore. So the use case for VaultDB, that's really high throughput, and that means not the fastest latency, not the fastest answer possible, but they're rather sacrificing a little bit of latency, but as much throughput as possible. And we're still talking about latencies that you don't feel in the web. So what they're saying, what it's very good for, is real-time analytics that are used for real-time results. I find a lot of similarities between VaultDB and Erlang, and this is why I called it a match made in heaven. They're both made for a concrete need. They're not the results like some competitors of probing around and then, oh, maybe it fits for this, or maybe, oh, it fits better for that. No, there was a concrete research before the product was even started to be created and experimented for. VaultDB is really made for distribution. It's really made for multi-core, not just trying to cope with a new situation that we have in the hardware market. No, it's made for that, like Erlang was back in the day. And it's also a truly different approach, pretty exciting approach, and that also is something that it has in common with Erlang. VaultDB, as I said, is corporate created and still open source, which is important. There is a for-pay enterprise license, and you do get some very good stuff. And if you're a big company, you probably will want that, and you will pay for that license. But quite honestly, the open source edition is so good and it's so complete that it's not a trick to just get you into buying. It's more like, if you really use it on a professional level at some point, you're going to want to have support and additional monitoring that you want to have on a professional level. So I think the main features of VaultDB are probably, as I said before, it's ACID. It's still SQL, and that is pretty important in some cases and gives you some flexibility that you lose if you lose SQL. But it's also about high availability, so that you don't lose your data and you can always be online. And as I said, it's about scalability. How they position themselves is pretty interesting if you look at the competitors in the market and what is VaultDB good for if I decide to look at a new database. Then if you look at different use cases of the age of the data, like on the left-hand side, you would look at very, very new data just came in, on the right-hand side on aging data. And if you look at the value that is in the data, how fast you can react to that new information that just came in, and the resulting value of all the aggregate data that came in so that you can get a big picture reaching back in time, then VaultDB is positioned on the left-hand upper side where velocity is marked. High-value data that came in very recently and that you want to have a fast answer for. And you see like Hadoop and data warehousing and traditional RDBMS are positioned in other areas there. VaultDB has, they're on the market for 3 years now. I guess their business is picking up. They have quite some customers now, but it's like Erlang, it's not well known in the mainstream yet that every IT student would know about it. Something interesting that this pie chart shows is that where VaultDB really did something new and really has something that is making it a different creature from, say, MySQL, is that they get rid of everything that you usually have to have in a database engine to write to disk. And that is a conscious decision, because Stonebreaker, who, as I said, was around when these databases that are now mainstream were created in the 70s and 80s, back then you just needed a disk to have all the data stored somewhere that comes from a normal, ordinary business. But today, the data that really comes in business, and that's in the area of gigabytes, fits into memory. And that was just not the case like 30 or 40 years back. And that's why all of the traditional and successful databases on the market, who are now changing into something that is also highly caching and in memory, have kind of the wrong architecture for the hardware that we have now. And by getting rid of most of the overhead that is in the internal architecture of most databases, they were able to get rid of, as they say, 75% of the usual workload within a database engine. A word about SQL. SQL is often derided, but if you look at it, it certainly has flaws, and the syntax might be awkward sometimes, but essentially what SQL is about is math. It's about the relational database model, and that's pretty sound math. And the advantages that have been found are not tied to the syntax as to SQL, but you don't want to lose those advantages, and that is at the core of it why VaultDB kept SQL. If you ever worked with NoSQL databases, in the beginning it's an interesting promise what you can do with it, but as I had on a previous slide, the strategic flexibility of then changing course is something that you might lose when basically all that you have to do a search or a query is your key. And very soon, if you really get down and have a project that you use NoSQL for, you will find yourself programming keys into programming indexes into your keys, so that you have multiple ways of accessing the data, and then after a while you realize, well, what I really would want to have are indexes. So that's why successful NoSQLs also offer new ways to index data. And that's why SQL is something you might be missing. In general, if you look at the database market and try to get an orientation about, okay, what database is worth it, that I look into it and what fits my needs, then CAP can be a good starting place. And you can group the databases in basically 3 groups, where the idea is that out of those 3 things, consistency, high availability, and partition tolerance, you will have to sacrifice one. Now that's highly debated. Even the inventor, Brewer, meanwhile has revisited that topic, and Stonebreaker is also very heavily protesting some of the conclusions that are drawn from that. But it gives you an orientation. And as I said, VaultDB is on the CA side, not entirely sacrificing, but being weaker on the partition tolerance side. So it's not elastic yet. They say they're working on it. But it's really consistent. It's not eventually consistent. And it's highly available in that it has a built-in replication mechanism. ACID, as I said before, why is that so important to me? Well, in games, at least if they're a little more complex, when you have that threshold, when you pass the threshold where players interact with each other, that's really it. Then you have the main data sets, the records, the player records interacting with each other. And then what you almost can't live without is double bookkeeping, because otherwise money gets lost, or swords get lost or duplicated if you have a crash. And you would think that ACID is really something that's for granted, but of course it's not. The NoSQLs, the companies that are pushing the NoSQLs explain to us why base, which is or eventual consistency, can for many business cases be a more interesting choice. For example, Amazon, where Dynamo came from, might care more about the other features that come with their dynamic structure, and they don't care so much about how fast the consistency is arrived. That is something that you have to look at with your application. If you're, for example, storing images, and each individual image is one data point, and the images are not interconnected, then you probably don't need ACID. But if you store some form of data that where it has something to do with each other, what the individual data points, the major data points are going to do, then you might find you need real ACID. So if you have base or eventual consistency, and if you go through it, you might find that it's really hard to emulate on a database that's not giving you ACID to have an ACID behavior. Because in a way, that's really what databases are for, to give you that. So how is VaultDB achieving what it can do? For one, they are compiling queries into the database core. I'll come back to that in a minute. Then they have single-thread execution. They call it transaction completion. That is something that is really close to what I find in Erlang, where to have a lock, basically, you create a funnel by one individual process, and that process is going to be the only thread that is going to access a certain resource. And that's how you make sure there's no race condition possible. One process is going to run over this code only, and that's it. And VaultDB does, in a certain way, pretty much the same. They need a little bit more information up front about how your data is structured and what can be expected, how it can be used later. And then it's sharded in a very intelligent way so that really what's happening is that per CPU core, one transaction is done incomplete, with all the data in place, with all information in place, that one CPU core on one machine of the entire cluster can complete the whole transaction. And that's kind of the magic ingredient, how they achieve the speed, because that's why they can leave all the locking away, because one processor core cannot race itself. And how they achieve that is in a pretty intelligent way, I find, that they are just looking at how does data really look, like real data. There's a common structure there, and that is that most of the time it has a kind of a snowflake structure underneath. Now, I remember the times when this guy was cool. It's a bit, that's a little bit of, for me, the dirty secret of VaultDB, that underneath, to be able to compile the stored procedures into the server core, you have to do a little bit of Java. And this is how it looks. You can see in orange, you can see the actual query of this hello world query. And this is the bit of Java you have to program around. In this case, pretty clearly, it's boilerplate. And I would think that VaultDB could go down the path and just generating that for you and doing it all transparently, and I kind of appreciate that they don't do that. Because the Java around your queries will stay simple, but it also gives you a very high flexibility when you need it. Because really, you have a number of Java classes, and you can do pretty much anything with it that you need. And the trick here, so to say, is that this way you are programming your anti-stored procedure. And like with stored procedures, you're kind of moving the calculation to the database server, and you're moving the calculation to the data, so you have them close. And that's why it can be so much faster. And an entire transaction with maybe 4 operations or more is this way executed right into the server. It's compiled into the Java server and the Java layer of the server, and it's executed right where the data is, with all the data in memory already. I had that. These are the petitions, and this is the information that VaultDB will need you to provide about your data before you start. And usually it's pretty simple. If we take, for example, an ordinary business might have customers, and those customers are the basic meat of the database, and the customer number is probably what you would start to have a hash over. And that's all. And then the individual slices are put on the individual clusters, cluster servers. And case safety is basically provided by putting slices doubly on different servers. So if one server node goes down, there's still a copy on another server node. Interestingly, historically, VaultDB started out with a leaderless architecture where each node in the cluster was equally right about what is true. And they found in practice that it made more sense for them to go back, I say go back, to a master architecture, because in practice, the ideas seem to be very nice and philosophically beautiful, but in practice, it can be a lot faster for writes and reads. There's a lot of performance that you leave on the table, especially for reads in a way, if you don't have a master. Now, the snowflake structure. That's something, if you imagine this snowflake is one customer and everything that is stored to that customer. And basically, all the data and all the tables that you have are pointing back to the primary key of the customer. And even if you have an order and then the items of that order, the items point to the order point to the customer. And that's what they call snowflake. And these snowflakes are usually the majority of data if you take a real problem. But then you also have some non-aligned data that doesn't fit into that snowflake. For example, that could be your portfolio, your customer, your product tables. Now, typically those product tables are not as big as your customer table. I mean, if you start out, maybe it's vice versa, but if you're an established business, you would usually grow and will want to scale most of all on the customer side. Now, what's happening if you store that data with VaultDB is that those snowflakes are distributed over the individual nodes of the cluster. And that could be the customer number, would probably be better than in my example here. The idea is you use the first letter of the last name of the customer. But by whatever criterion, those snowflakes are distributed. And the non-flakes are replicated. And that's one of the other pretty intelligent tricks that VaultDB does. If you have your product portfolio replicated transparently for you as a user across the entire cluster, then that makes sure that individual transactions are much more likely to be completable within one core, because every core has direct access in its memory to the entire product table. And whenever you update that product table, which is something that would usually happen much less than updating a customer somewhere in the system, maybe if you think about it, it could be one to a million times less, so it's a much slower data flow there. Then VaultDB does that transparently for you and makes sure that all the tables that are replicated across the cluster have a consistent state again before the other transactions are kicked in again. And that is something that in a certain way makes VaultDB more SQL even than SQL databases. Because if you go about designing a database, very often I find that in the back of my head, I already know what I will optimize by doing in the application instead of in the queries. Because certain things I know is just going to slow down the query, and I can do them much faster if I have a lookup table in the application. For example, the product code. And with VaultDB, that optimization makes no sense anymore, because it's so fast on the server side, and it does exactly what you do to optimize on the application side, that you can write it into the query. Because the product code is going to be a C table in memory in VaultDB 2. And you can't even optimize that. And what happens is that your SQL is going to be cleaner. And that's something that we found doing a real moderately complex data structure. We found, well, certain optimizations don't make any sense anymore, and the tables look cleaner. That was a find that was kind of an indication that they're doing something right there for me. So yeah, VoltDB meanwhile has drivers for a lot of languages, and now it also has an Erlang driver, and actually I'd like to sort it like this, I guess. And this is how it looks. That first is an insert call. That's actual Erlang using the functions of VoltDB. It's pretty easy, pretty straightforward, and it's not more complicated than you would otherwise access your data. There's a select down there. That's also going. It's modeled pretty much after the Java reference API. And this is a hello world. That's actually the complete hello world. It's actually exactly the hello world that you would be executing if you executed those 4 lines where I said you can install and try it right away. What you see here is simply just the application is started up. Then you have to create a pool. And a pool of connections in VoltDB is something where every server of the cluster has its own line to your client. And that's important for distributing load also right from the client. So that's why you have the concept of a pool. There would usually, if you connect a cluster, there would be a list of the IPs or the domain names of the individual servers in the cluster instead of localhost. Then you query the result, and actually select, in this case, is the name of the stored procedure. It's not SQL, but it's what we saw in that example about the Java, a little bit of Java. That was the select stored procedure, and that's called here by name. And then we get a result back. In VoltDB, there is no idea of a stream of a result coming back, because usually in OLTP you'll have short requests and short answers. And what's coming back is a complete structure, and that is then analyzed using functions that LVOL provides. And in the end, you close the pool, so it's really easy. I did a benchmark using that driver. And I was super happy to find that the driver that is native Erlang doesn't only perform as good as the other drivers, but actually I had done a benchmark before for the Node.js driver that's programmed in C. And for all I saw, the Erlang driver is in a lot of places faster. So it really shows how good Erlang is in bitmap pattern matching and bitmap decoding on the lowest wire level. So what I did there, I think the most important number is probably that you have around 25,000 transactions per CPU core if you use Amazon's cloud. Now, Amazon's cloud is really slow for some things, and I think this benchmark would run a lot faster if I had as many cores to use and really have them installed somewhere as real machines. But this benchmark is what you could very fast do yourself. And actually, I listed the prices here. So if you sign up to Amazon and just do this benchmark yourself and then maybe play around a little bit to make it closer to what your application might be, it really doesn't cost a lot, and you can really try it out on a real cluster. And the benchmark I used is like the example that you would find scattered all over the VoltDB blog posts and manuals. And it's an example where we play American Idol or any TV show, and then users all phone in within a couple of minutes, so we have a huge peak on the database. And then you want to have the result really fast. And that's exactly what this example is made for. It's exactly where VoltDB is positioning themselves. And what's actually happening is in the benchmark, the emulation goes like I'm just fire hosing the server with a lot of clients, and millions of calls are going in, so to say. And there's a small set of candidates, like a half dozen, and there's one transaction basically per vote. this is the table structure for that benchmark. Very simple. It's just the contestants, then the votes are counted. The contestants are 6 or so, and the votes are millions. And then, to make it a little more interesting, there's an area code added where there's a lookup what state, American state, and certain American area code would belong to. And these transactions that I listed there are really 4 operations. And that's not a cheat or so. It's really 4 valid operations where first they're looking up, okay, is the contestant that is in the call, named in the call, is that even a valid contestant number? Then they're looking up if a person has voted before. So that's a real read across the entire database, theoretically. And then they're looking at the area code, and then when everything's fine and they found that, then they store the actual vote. So that's happening per transaction. And that's why the numbers, if you look at them, of 877,000 transactions per second, that's actually 3.5 million operations per second. So yeah, these are the resources. If you're interested, you find the slides in the internet. I've listed where you can download Errol Vault. I've listed where you can find more information about the benchmark. I've wrote up a post about it, and that's something that I hope anybody could just use to just, as we did in the tutorial, just sign up for an EC2 account and just try something out yourself in a real cloud cluster situation to understand where could this be going, what I'm doing. And again, this is what I'd love you to try out. Drop me a line if you've run into any troubles. The maturity of the driver right now is, I'm giving it a 0.3. So there's some way to go, I guess, but we're having very good results. During the benchmark, it was very stable, and I'm very happy that Robert Verding said he's interested in looking at it and is already giving me some feedback where we can improve it. So yeah, I think this could be a very exciting thing there. And if anybody feels like he wants to look into that more, it's on GitHub. And please don't hesitate to contact me, and right after the talk, talk more about it. And if you can become a contributor, that would be wonderful. Thanks a lot.
Brilliant. Thank you very much. Any questions?
In the example that you show with the select query,
Yes?
the row object that you then extract the column information from, what is that? Is it a port, or an open port, or a socket, or what is it?
You were talking about the Erlang's code, yes, or the Java code?
Example. Yeah,
this one? Or this one?
No. This one.
Okay, and the question was, which object?
You have the row variable there, so
right.
You get a row, and then you start extracting stuff with this get string from the row.
Yes.
So what is the row? I am assuming you are actually streaming data out of the row, or the row just is an Erlang term with everything on it?
Pardon? Can you say that again?
It's
a record.
The row? Is already an Erlang term with all the information on it, or is it a port that you're reading from, extracting the info dynamically?
Yeah, thanks for that question. So, as I said, there's no concept of streaming here. It's a record with all the answer. So it's not very good to return big answers of huge lists. You can do that to a certain extent, but not reading out the whole database like this. And that's because OLTP is made for that. And like the voter example, you have very short pings of very short writes, and you also have very short answers. They're complex, but they're short in their result. Yes?
Okay, I have 2 questions. The first is about, you mentioned memory, it's fast, it's 100 times faster than MySQL because of memory. And then the next slide you said that's fully persistent to disk. So how does that work?
That's a very interesting question too. And I think VaultDB, my personal opinion is they were very lucky. They found something really great. The original architecture of VaultDB was lyrically said that they had some kind of a rhythm in that they were synchronizing their system. And it worked a little bit like this. Every core kind of takes in transactions and then waits a while until it can be sure that no transactions will come in that are earlier than what it in the moment has in its list. And then they are executed as a chunk. And that created a kind of rhythm in the system where there was always a stop. And that is also what creates a latency of a couple of milliseconds, because they're always waiting to make sure that all the cores are synchronized without the cores talking to each other. And then they found that during those wait times, that's a great opportunity to write the stuff to disk. That was not planned for at all. In fact, I spoke with this former CEO of VaultDB, and he told me, yeah, they were really insisting on being an in-memory database, right? Just like Bigtable. It's all, I don't know if that's even true of Bigtable, but it's like, it never goes down. You have replication across individual clusters, and you really go by, I don't need a disk. I have it all in memory, and I have it multiple times. And that's my safety. And for a whole data center to go down, that was said to be not so likely, but that was absolutely not bought by the customers. Everybody hated that, myself included. I thought it's really stupid to develop something this way, because you always have to ramp up the database again instead of having it on disk nicely. And so they understood they had to change that, and they had snapshotting from the start, so it wasn't they didn't really start from scratch, but they found that they have this opportunity there in those stops that are there for the synchronization, that without losing a lot of performance, they're losing a little bit, they can write it all to disk. Now, that's not literally true anymore, because they changed the hard architecture, the architecture in the center of it, but as a metaphor, so to say, it's still true. And you can either get an OK back if it's stored in memory or when it's stored on disk. But what's important to know there is that I/O controller will very often tell you stuff that's not quite true. And if you don't have a battery I/O controller that is going to be able to write to hard disk even when you have a power failure, then even the OK from the I/O controller that's on disk now is not going to save you. So it's a tricky area there where.
Does that mean that the size of the database is limited by the size of memory you have? You can't have a DB bigger than memory.
Yes and no. And the third part is I don't really know very well what they are at now. They started out like that. And as I said, memory now is so big that for most use cases, you don't need more than fits in your memory. And you have a cluster. Don't forget you have a cluster, right? So it's, and also this benchmark was, I used several computers for that, like 10 or so. We all had tens of gigabytes. And for a real application, at least for what I would do there, that's all I need, really. But I know that they were working on being able to store more than fits in the main memory. And what I don't know is how far they are.
Cool. Thank you very much. Probably out of time. Everyone's probably hungry. Oh, go on then.
Do you know any ORM which support VaultDB? For example, Hibernate, maybe?
Pardon?
ORM. Hibernate.
Can you repeat? Just.
Do you know any ORM which support VaultDB?
No, I don't know. You mean ROM or what? Flash ROMs?
ORM.
Okay, thanks.
And have you thought about creating ORM for Erlang, maybe? Is it a good idea?
Actually, I'd appreciate if you just shout the language. I can't hear you.
Object-related mapping.
Yes. If that exists. Not that I know of. Not that I know of, which really means it may be, it's just something I didn't look at, obviously, looking at Erlang with it.
Cool. Thank you very much.